Good afternoon or good morning. Thank you for coming to my talk. My name is Ignat, and we'll talk about TPMs and the Linux kernel today. I work for Cloudflare. Who here knows Cloudflare? Okay, I'll not explain what we do then. Yeah, but myself, I do Linux at Cloudflare. I'm actually a die-hard Linux fan. That's why I'm presenting from a Mac, because I know you can't trust Linux do two things: power management and connecting to projectors, right? so, yeah, I'm passionate about system security and performance, and I enjoy low-level programming, Linux kernel drivers, bootloaders, and other stuff, reading in unsafe programming languages. So I'm really disappointing having Rust in the kernel, actually. It's not fun. Yeah, but today we're going to talk about TPMs. Who here knows what a TPM is? Yeah, many folks. Small recap. So a TPM is a small chip, security chip, present in modern laptops and servers alike. Most of the time it is a discrete security chip. I know like some modern CPUs have like an FTPM, which is kind of like on SoC version of TPM. It's usually passive, non-intrusive, so it doesn't like hook into your memory or like messes with your CPU. It only responds to commands. So if you ask it to do something, it will do it for you, but if you don't, it will do nothing. So it's kind of like, it's not an invasive NSA device which spies on you. But even though it's passive and non-intrusive, it's a building block and foundation for platform integrity, authentication, and remote attestation. And as the primary function of a security chip, what it should do, it should handle cryptographic keys and can do some crypto, right? So this is what TPMs are doing. It can handle cryptographic keys. If you ever read or went to a talk about the TPM, most of the time when we talk about TPMs, we talk about a thing called remote attestation, right? So like where the TPM is a basic foundational block of it, so, and it allows you, the remote attester, to actually remotely validate the integrity of software and firmware running on your system. So this is what the TPMs are most useful about, but this talk is not about it, so I don't want to repeat it. This is a talk about using the TPM from an application perspective. Like, let's say I'm an application developer. TPM, like if TPM is present everywhere, why can't I use it and like get hardware security support for my application? And yeah, and can I store my keys in the TPM and use them without exposing the key material to the main memory? Basically, who just been downstairs to the memory address space talks? Yeah, so you kind of understand now why it's important, right? Because if the keys are exposed to the main memory, it's in your process address space, right? And if something goes wrong, your application is compromised, the attacker can get those keys from memory. If they're not in the memory, it's much harder to actually do harm. So yeah, TPMs are present everywhere in every standard computing device, but there is almost no actually application support for storing keys in the TPM. Like SSH doesn't do it. I don't know, GPG doesn't do it. Like many things don't do it. Like almost no one is using it. So why, right? And to understand that, like there is some complexity of interacting with TPMs on modern operating systems. So as an application developer, this is my mental model, right? So I write code. I want to use TPM, right? Simple and easy. This is where I want to start, right? But when I start digging into it, turns out it's not that simple. Of course, my application is running on an operating system, so I cannot interface with hardware directly in the operating system, so I have to use through hardware operating system level abstraction, and on Linux I have to interface with a special device created by the operating system, right? Okay, but this is not it. So apparently what I also need is a thing called a resource manager. So TPMs are useful because they're very cheap. That's why everyone's putting them everywhere. But on the other hand, they are very low power devices. So they cannot handle, like on modern operating system, you have many applications. So it's a multitasking system, right? But TPMs cannot handle concurrent requests, or they can have only a limited amount of concurrent requests. So the way how people solve that is like you have some kind of proxy, which is called a resource manager, which kind of like serializes access from multiple entities to the TPM, so TPM can process the data properly. Right. So I need that, but again, this is not only that. I also need a TPM library, right? So because to communicate with the resource manager, there is some kind of an API, and to abstract it properly, I need a high-level library. And like the blue thing is the hardware, right? The yellow thing is provided by the operating system, and the purple thing, the green thing is what I write myself, and the purple thing is my third-party dependencies, right? So let's actually zoom into the resource manager, and it's actually a little bit complicated there as well. So the first iteration of the resource manager was a user space daemon. Which was very confusing for application developers. So now, just to talk to a hardware device, you need a user space service, a systemd service, to mediate that access. Like, what if that service is usually written in C? Like, what if it crashes, right? So like, well, you can't talk to a TPM if some service is not running, which is really confusing for the application developers. Later, like the kernel community actually recognized that problem, so they created an in-kernel resource manager. So now, on modern Linux, instead of interacting with dev TPM, you interact with a dev TPM RM0, which RM stands for the resource manager. It's inside the kernel, so it will do most of the resource manager work, and it's always there, like as long as your kernel doesn't crash, of course, right? But if it does, you have bigger problems. So yeah, these days you can kind of get away with an in-kernel resource manager. But if it goes, now let's zoom into the TPM library, and this, like the ecosystem is not great as well. So we have two major competing implementation, which is like Intel TSS, a trusted software stack, and we have the IBM TSS, trusted software stack. And the problem with these, they have completely incompatible APIs. So like if you want use one, you cannot switch to the other. And this is where, if I'm writing like, you know, an application for Linux, like I need to select it beforehand or write a complicated abstraction layer. Yeah, but if I just pick one, like maybe my software will not work on every distribution, because some distributions might either package one or the other, but not both, right? Also, there are some languages which are more, you know, opinionated, and they say like we don't even like the external dependencies. We will write our own stuff. So it's like Google, for example, they wrote the Go TPM, a pure Go library to interface with the TPM for Go. And I imagine, I haven't researched it, but I imagine something is similar happening to Rust. Rust probably also there are crates out there that interface with the TPM. So yeah, now you have all this complexity of like you need to think about resource managers, the TPM library, and yeah. So for example, this is a snapshot from TPM2 software stack from their official GitHub page, showing all the components of this TPM ecosystem, which you as an application developer somehow need to understand, so you can interface with different things on different layers, and you have to actually pick the proper one for your use case, which which is really confusing. Like it's like only a small amount of people in the world actually understand for all of that, right? But okay, you will do your research, you will do everything is ready, your code is ready. The problem is, if you try to run your code, you'll still not be able to do anything, because if you try to interface with a TPM or a resource manager on Linux, by default, you'll not be allowed to do so, right? So, and the reason is because, well, this is my like a very standard bare bones Debian installation. So by default, both the TPM and the resource manager only allow root to access it, right? So confusingly, if you do install a IBM TPM software stack on Debian at least, well, it will do something, but turns out, well, that your TPM devices now can be read and written to by a special new user called TSS, and the resource manager can be also be accessed via TSS group. So, well, it's better, right? So your application can be in the TSS group to access the TPM, but then you have to properly package it for a particular distribution. And for example, if your application is in Go and using Go TPM, do you make a dependency to the TPM2 tools, which are C, just to get the TSS user group created so you can join the group? Yeah, yeah, the interface is a mess, right? So it's very hard to get to the TPM from a regular application code. What if there is another way, right? So, and this brings us to Linux kernel key retention service. Who've been here last year? Yeah, last year I actually did a very comprehensive talk on the Linux. I call it the Linux Key Store. All the bits and pieces. I will repeat some of that here, but basically, it's a service inside the Linux kernel which allows you to store and manage cryptographic keys and secrets. So the way how it works is of course, you have multiple applications, you have your kernel. Yeah, and it provides you basically 3 system calls like AtKey, KCTL, and RequestKey. And for example, applications can use these set of system calls to put keys or secrets inside the kernel, inside the kernel address memory space. And the nice thing about it, yeah, and was originally developed for in-kernel crypto services, for example, disk encryption. So the disk encryption and decryption of data happens inside the kernel, but the application needs to provide the key to the kernel, so it uses this set of system calls to do disk encryption or file system level encryption. But later it was extended, so the applications themselves can use a system call to manage these keys and provide the cryptographic operations. And the nice thing about when you put key inside the kernel, it becomes a full-fledged kernel object, right? So it has associated permissions and other stuff you get from kernel entities, right? So internally, the keys are key objects are categorized into key rings. So key rings are like a collection of other key rings or keys. So yeah, a key is like a file on a file system, but a keyring is like a directory. But the difference is that, for example, a single key can be present simultaneously in multiple key rings. And key rings actually define the lifetime of the key. So for example, if the key is not present in any of the key ring, so you detach it from the last key ring, the kernel securely destroys that key. So it's not only frees the memory associated with the key, it also zeros the memory properly. So and this is also very useful for if your software is written in high-level language with a garbage collector like Java, because zeroing out keys in Java and even Go is not a solved problem. And if you just store your keys inside the kernel will automatically do it for you, and you don't have to deal with that, and you don't have to fight the whatever that garbage collector pipeline is doing. Yeah, and if they're also securely destroyed even if your application crashes. One simple example to get you a taste of what a Linux key store looks like. So imagine we have a Linux system with 2 users, Alice and Bob, and as you can see, they don't share any shared credentials. So they not part of a shared group, nothing, 2 different new users. And so what Alice can do, for example, let's say Alice wants to share a secret with Bob. So Alice can create a secret, this is her secret, Hunter2, and she can put it into the kernel key store, and all the key store objects are represented by unique serial numbers, so you get the serial number back. So what Bob can do, Bob can actually, if Bob is expecting a secret from Alice, what Bob can do, Bob can create a new keyring, and he will also get a serial number. And what Bob can do, Bob can set permissions on that keyring, which basically allows any user on the system to write to that keyring. And writing to a keyring means putting keys into the keyring, right? But not reading even from that. So then Bob can communicate his keyring a serial number to Alice, and Alice can move her secret to Bob's keyring easily, right? And then Bob suddenly can either access the secret information. So Bob can access the secret because Bob now possesses the secret created earlier in Bob's keyring, whereas because we moved it, Alice cannot read the secret anymore because Alice does not own the secret. So this is how useful the kernel key object is. You can play with permissions to get really fine-grained access control to your secrets inside the kernel. With respect to keys are categorized with several types and they have different properties. So the simplest form, which we just saw in the example, is we call the user key. So the user keys, imagine there is a process, it has some kind of secret or a key. Basically, yeah, we call it a plain text cryptographic material. What the process can do, the process can put it inside the kernel, and another process, if it has permissions to do so, can read that secret back. So this is what Bob did, right? Or the same process can read it back. There is another key type called logon key. So logon key starts the same way. So a process has a secret, the process puts it inside the kernel, but the difference from the user key is once it's inside the kernel, nobody can read it back at all. Yeah, if you don't, even if you have access, you can never read this plain text material back from the kernel. And why it's useful? So yeah, it's actually useful to share secrets with the kernel itself or in kernel cryptographic operations like disk encryption. So for example, if you run a modern Linux distribution and you use full disk encryption, you would see that when you unlock the disk, your password is actually shared with the kernel via a logon key. There is also an asymmetric key type. So imagine, unfortunately, the kernel only supports RSA keys at the moment. So you have an RSA key. One process can put it inside the kernel, and either the same process or another process which have appropriate permission, they don't need to. That process does not have to read the key back, but they can use that handle of the key and perform cryptographic operation like decryption with the private key part, like decryption or signing, right? So it kind of like imagine like the kernel becomes this like simple software HSM for the stuff, right? Yeah, and the nice thing about it, like these are just system calls available to any process on the system with no extra permission unless the ones set by the processes themselves for their key objects, right? But anyone can access these system calls. So the question is like, would it be cool to combine this stuff, which is like a software-based HSM, and the TPM inside your platform into one single entity to get like something closer to a hardware HSM? And Linux already kind of did that partially. So there is another key type called a trusted key. So the problem with all the previous key types that there is still a moment in time where a plain text cryptographic key is present in some process user address space, right? So like how can we ensure that the keys are only in plain text available in the kernel address space but never available to user space address space, which is because most processes, most code is being compromised as a user space process, right? So we have a wrapped key. So imagine you have some plain text cryptographic material you can share with the kernel, so you can out of band encrypt it to your particular machine's TPM and create an encrypted blob. And if you provision it as a trusted key, so when you put it inside the kernel will automatically use the TPM and unwrap the key inside the kernel address space. So inside the kernel address space, it will be the plain text cryptographic material, and here it's an encrypted blob. And when you basically try to read it back, the kernel will automatically wrap it again. So like you cannot have a plain text cryptographic material in user space, right? Which is very handy, but originally when it was introduced, it wasn't very useful, right? So like if you have a key and it's only in plain text in the kernel, it's only useful for this one particular use case of sharing the key with for disk encryption. That's it, right? So turns out actually Linux has a like the key store is one subsystem, and Linux has a Linux Crypto API which is a different subsystem. They're kind of like working together, but they're not part of the same subsystem. They have different maintainers. And the Linux Crypto API is actually interesting in the sense that you can use your Linux kernel as a crypto library, right? So like if you want to just encrypt some data and you, like, let's say you're running on a very low-end device where you only have Linux and your application and you cannot even afford to link OpenSSL, so you can ask the kernel to do encryption for you without having any crypto code in your application. So what you can do is the process can create a special socket type, but it's not a network socket. It's called a crypto socket, and the socket is basically a communication channel between your process and the kernel. And the kernel internally will create a crypto algorithm instance inside the kernel address space. And then what the process does, the process provides the encryption key to the kernel, and the kernel will put it there, right? And then when you want to encrypt or decrypt some data, you kind of like similar as a network communication, you send some data to the socket, like plain text data, and you can read the encrypted data back. The problem with all this, as I mentioned, it's not part of the Linux crypto key store subsystem. So this key is not like a kernel key store key. It's just a buffer with plain text bytes. So basically, we try to close that gap, and what we did, we submitted a patch to the kernel that combines the Linux Crypto API with the Linux key store, so they can work together. So, for example, you have the wrapped key, but let's say another process is given access to use that key, but the process can never read the key back. So what the process can do, it can create a crypto socket, right? The kernel will do the same thing, but instead of providing the key material directly in a buffer, the process can just reference an existing kernel key store by its serial number. So if this process instantiated the key, that process, if it has permissions, can say, hey, instantiate this crypto socket with the key from the serial number. And then, because inside the kernel space, the kernel has access to the key because it's in plain text, it can basically do that. And yeah, and then this process can actually encrypt or decrypt data with that key without having access to the cryptographic material itself. Yeah, but it's available from Linux 6.2. So if you're using an older version, you're screwed. Yeah, one downside of this approach is that basically wrapped keys are byte blobs encrypted to a TPM, so they can only technically be considered as symmetric keys. So you cannot actually do signing or like private key operations. So you cannot literally wrap an RSA key and then use the same thing to use that key inside the kernel as an asymmetric key. I actually wanted to submit a patch for that, but turns out there is already work going on to do it, and well, it kind of does same but not the same. So this patch set, which is supposed to have been merged to 6.11 kernel, which is about to be released, but as I looked, it wasn't, so I guess it wasn't ready, so we have to wait more. But what it wanted to do is like, well, you basically take the asymmetric TPM, the asymmetric key model, and like transition it to the TPM instead of like the software key. The way how it will work, right? You have an RSA wrapped key, you put it in the TPM, and the kernel will not unwrap the key, but it will instantiate it inside the TPM. So like when another process wants to do like signing on decryption, it will go to the kernel, and the kernel will forward that request to the TPM. Still better, because now, again, to access the TPM functionality, you technically don't need any, like being in a TSS group. You're using like the standard key store sysctls, but your private keys is backed by the TPM, by hardware security. But both with symmetric wrap keys and asymmetric wrap keys, there is one problem which needs to be, well, not needs to be, but sometimes it's not very convenient. and the problem is the state. So generally, if you zoom out and see how wrapped keys work, so the way how you create them, you use a random number generator, right, to create a new key. So you generate a key, and then you wrap it for a particular TPM. So you create an encrypted blob. But this is where, and yeah, you can put that blob inside the kernel, it will be unwrapped. But the problem is the key store subsystem is kind of, it's in memory, right? It's ephemeral. It doesn't have any persistent storage back. So you still are responsible for the key management itself. So like, you need to have that wrapped key available. So like if you generated a key for your application, you have to hold on to the encrypted block because if you lose it, will be nothing to put inside the kernel to unwrap it. And like after every reboot, you have to reinstantiate the key because the kernel doesn't keep the keys on disk or whatever. So you have the problem of key management and mostly like key storage. You have to store it somewhere. And this kind of makes the whole concept not very useful for like diskless system. What about diskless system? What about if you store all your keys and you have a broken disk? So you now have to think about data backup and like keys backup. Like what if you, like in Cloudflare, we consider our servers what we call ephemeral. So I can take any server, wipe it, and it will start in clean stench. So like what if I wipe some keys, right? So accidental wipe is a problem. And there is also the scalability problem. So okay, we're talking about applications, right? And like there are many applications running on Linux. So yeah, like each application needs to do this. So like you have like one key for one application. Like if you have five keys. You have blah blah blah, like gazillion of keys. Like if you have many services running on the system, so you have this extra, well, considerably large and like very critical state, because these are your cryptographic keys which give you access to your data that you have to manage. So what if we just change the whole thing and try to do it differently? What if we, instead of wrapping the keys, what if we like create them a little bit different? What if we derive them? So let's say we take the TPM, which we already have, right? And every TPM, if you read the spec, they have a seed. Well, technically they have 4 seeds, but for the purposes of this talk, like it's enough to say that it has like a secure, strong seed for every key it uses, which is unique to that TPM, and you can never get access to that seed. There is no TPM commands which allow you to read that seed. So it's only inside the seed. But the way how you use this seed, the TPM has also a key derivation function, so you can use the seed to derive keys from the TPM. Yeah, and it's kind of available in every TPM. So that whole thing is a part of TPM stack. If you have a TPM, you expect it to have that. And like the algorithms are well known, and you can actually predict that. So what we can do is we can take like an application specific info, which doesn't have to be secret. It's some application metadata. It just has to be unique to a particular application. And we can actually feed it to that KDF and get an application specific key, right? And the nice thing about it, this thing is like perfectly scalable, because, well, as long as you find a metadata which is unique to our application, you can like create many unique keys, and these keys will be unique for every application. And the nice thing about that approach, this state is totally disposable, because the whole process is reproducible, right? So as long as you have access to the TPM and its seed, and like your application metadata, which can be just some static thing about your application, you can always recreate all your keys, right? So for example, imagine if you use this approach, let's say you have a very small router, right? So which, well, doesn't have any storage, right? But you still want, when you SSH into it, you want to have like you don't have to reaccept the SSH public key of your router, because after every boot it changes, because it doesn't have anywhere to store it. But if you use that model, you can have a router static SSH key, and you can kind of like, as a router identity, easily use it. So how do we use this? So one thing I mentioned at the start, there are actually 2 system calls to instantiate keys in the Linux kernel key store. It's called AtKey and RequestKey. So far we have seen like AtKey examples, but the overall semantic difference is the following. With AtKey, the process or the application is responsible to provide the cryptographic material to the kernel. So yeah, the process calls AtKey and the kernel instantiates the key. If it's a user key, this is a plain text cryptographic material. It's a trusted key, it's a wrapped encrypted cryptographic material, but still the process itself should provide some bytes to the kernel, right? And with request key is different. The request key process basically says like, hey, I don't know what my key should be. I know it has a attribute of like some name, right? Let's say it can be an arbitrary string actually. You can say like SSH, right? Give me a key with an identifier of SSH. So it says like, this is why it's called request key. It's requesting the key from the kernel, right? So, and the kernel is supposed to like get these key bytes somewhere. Well, obviously the kernel, like everyone's setup is different, right? So obviously your specific kernel doesn't know where to get your keys from. So this is why the kernel needs a user space helper to do that. So the way how it works, like when the process called request key, the kernel creates like an empty placeholder in the key store, but then because it doesn't know how to get the key bytes, it calls a different user space process specifically located as being request key, passes as key ID, and this user space process is responsible to find that key from somewhere. And again, everyone's setup is different, so technically you as a system administrator can like plugins to that process which kind of resolve keys depending on your architecture and infrastructure setup. And like one of the plugins which I try to write is basically, why don't I write a plugin which gets the keys in the way I described from the TPM, right? So like you can forward that to the TPM. The TPM can generate an application specific key, then basically it returns to the plugin, then the plugin notifies. So yeah, we have an application specific key, and that user space process returns it to the kernel, so the kernel actually instantiates the key store object and notifies the application that the key is successful. So this is very useful to actually integrate this whole schema which I proposed into the kernel and the key store. Yeah, I'll share the links later as well if you want, but I wrote this plugin. It's a proof of concept, so I'm sorry, it's written in Python. But it kind of works. Yeah, and it generates application-specific key based on some metadata. If you want to try it out, you can go to this link from my GitHub, download, and the way how you would and you need to configure it. You basically need to configure it as a plugin to the request key user mode helper. This is how you do it. Don't really bother with all these things. You can read it on the documentation later, but it's important how it works, right? So like once you configure it, any process can request application-specific keys from the TPM. So for example, I will use just a keyctl utility, which is a wrapper for scripts around the kernel key store API. So here I'm actually requesting a user key with a string ID TPM2 derived, right? And I give like the key name will be test, and the 32 path thing, it means it's the way how I structured my plugin. So 32 means I want to like a 32 byte key, for example, for IS-256 encryption. And this is where I say like which application metadata my plugin should consider as like unique application info. And here I say path, right? So like in my setup, I say like, regardless of your code, like each executable, a different path will have a different unique key, right? And then you can, it kind of works nicely because you can protect that by file system permissions to ensure the keys cannot be leaked, right? So for example, we instantiate that key, we get some key material. Because it's a user key, we can actually read the generated key back. So like we'll see that we have some bytes from my TPM. Now I'm actually going to delete this key. You see, like I'm deleting this serial, so it was securely destroyed by the kernel. And then I repeat basically the same request. So, and you can see I'm actually getting, from a kernel perspective, I'm getting a different key because the serial number is different now. But if I read it back, I'm actually getting the same bytes. So because the whole process is reproducible, I'm deriving the same key for the same application which is present in user bin KCTL. Right, so let's delete this again, and let's actually make sure my stuff works. So like, let's move my executable from user bin to my home directory, for example. So it now has a different path. Again, I repeat the same request with all the same parameters, getting a different key, but now when I print the bytes, I totally have a different key here, right? And also, like, I thought about it, like, what if I do it from, like, you can protect the executables by path, but technically, usually it's 755, so every user can execute any executable, so I don't want to, like, let's say SSH daemon is running as root usually, but you, as a user, can call the SSHD binary and probably get the key generated somehow. So as an application metadata, I'm unconditionally considering the user ID as well. So if I rerun basically the same command but from a different user, I will get a different unique key. So like, keys are also separated by requesting users. There is a second mode which I implemented, which I think also might be useful, is basically, instead of the path, what I want to ask the kernel key store to consider is the application checksum. So instead of the application-specific metadata, which will be actually the code that requested the key, the text, right? Which is really interesting. So we can generate the key and we can read it back. We get some bytes, right? And in this case, again, I can delete the key. And in this case, I'm moving my keyctl utility from one path to another, right? And I'm repeating this request, but now I'm getting the same key back, just because the uniqueness of the key depends on like the hash of the code which requested it, which is cool. So like, technically, you can bind a unique key to your particular code regardless of where in file system it resides. Yeah. And to show that it works, actually, I did some research, and the keyctl utility has a bad message string, which is basically some error code. So what I'm trying to do, I'm patching my my executable and replacing bad message with bad massage. I patched 1 byte, right? But the application will still work. It's just an error string. So if I rerun the application with the same parameters, you see that the key is different completely, because now the code is different, right? So you cannot kind of steal the key from another application this way. Yeah, technically you can do the same way with asymmetric keys as well. So like, instead of user key, you can request an asymmetric key. You cannot read the asymmetric keys back. You can only do stuff with them. So what we can do here is we can generate some random hash and actually use that asymmetric key to create a signature, right? So we can now remove that key. We can recreate it again, so the serial is different, and we can again resign that. And because internally, by default, the kernel uses RSA PKCS1 signatures, the signatures are static, so therefore you see you get the same signatures for different keys. Therefore, the private keys are the same. So like, again, totally reproducible and easy. Yeah, so the only downside here in this architecture is still that with this user mode helper, still there is a point in time where the key is exposed to user space, right? It's much better now, because like, it's not exposed to my main process address space. It's exposed to some other process address space, and as bin request key is usually like self-contained and not network facing. But like, what if we can do better? Yeah, what if we can remove that plain text key from user space at all? So instead, why can't we just implement the same thing inside the kernel, right? So like, instead of going through user mode helper, we can just directly ask the TPM to generate this key or derive that key in a deterministic fashion, and it basically, the plain text will always be only in the kernel space and never accessible to user space. And some time ago I sent a V1 patch set implementing this. Well, I really try hard to explain this use case, but one of the responses, like, I don't honestly believe that this will ever be a solution for any possible problem that exists on the planet. I'm thinking of submitting V2, but this is partly why I'm presenting it here, because I know here as people who mostly work with IoT devices, a stateless system, like, would that approach be useful? And I want to get some feedback and maybe some, like, summed up points that it's actually useful. And yeah, so conclusions, interfacing with TPMs is hard, and this is why applications and developers avoid them altogether. I think Linux kernel key retention service can be a good layer to abstract away the TPM interaction complexity for applications, but as you just seen, some additional development is needed, and probably inside the kernel. I strongly think that TPM-derived keys is a good alternative to TPM wrap keys, providing like similar hardware backend security, but with potentially easier key management. And basically, if you want them now, it can be implemented via RequestKey plugin for the current kernels. But if you want a fully in-kernel version, you probably need to wait if I manage to push my patches through somehow. Yeah, and exposing TPMs through a Linux kernel key store can provide applications with like a really straightforward path to adopting hardware security without not much exposure to TPM internal. So kernel will handle all of that. And it's kind of probably for any other security chips. I know some devices or phones have other things, yeah, and I think like if you're trying to put some security chip in your hardware, like consider exposing its functionalities through Linux kernel key store. It gives you like this generic API that applications can depend on, and then like they can easily utilize your hardware. Yeah, so these are links for stuff I mentioned in this talk. So the first two ones are linked to kernel documentation about the key store and different key types. The third one is linked to the patch set, which should implement the RSA key inside the key store backed by the TPM. Follow that development if you want to know when it's actually being merged. The fourth link is unwrapped link to my RequestKey plugin in Python, which implements TPM-derived keys. And the fifth link is to my patch set, which actually implements TPM-derived key inside the kernel. Yeah, follow that if you like this work. Thank you very much, and I'm happy to get some questions. Yes? Yes. This is a good question. Yes, so yes, correct. So like, let's say for the user space version, right? If I have access to the TPM, like say I'm root, I can of course fake the comments of what the plugin does and say like, hey, generate me a key for that application at that path. You can like recreate that. So like, but it's kind of reserved for privileged application. You have to have direct access to the TPM to do so. No. Like, if I want to steal a key from other application, I have to be privileged. But if I just want to generate the key for myself, I don't have to be privileged. If they have the same metadata, they will have the same keys. But this is like the way how you set it up. You have to ensure they have different metadata. And for example, if they're two binaries and they have different code, they have different keys. Or for example, like the path thing I was considered for SSH server, right? So like anything that is present at like user sbin sshd will have access to the key, but this is a privileged path. So you cannot put any executable there, but you can, for example, as an administrator, you can replace OpenSSH with Dropbear, and they will have the same like key, right? Yes, exactly. Yes. Yes. In my example, it happens inside the kernel. So the TPM is only responsible for unwrapping the key. So you have a software plaintext ASCII inside the kernel, and then the kernel does the encryption itself. So it should be relatively fast, barring the user space kernel communication. Yeah. Any more? Yes. Mm-hmm. So yeah, it's a good question. That thing is also like it depends on the algorithm, right? So like for stream ciphers, for example, you can once you instantiate the socket, because it's a stream cipher, you can actually encrypt in chunks, right? So you can like send some small amount of data, get the decrypted bit, then send another one, then send a thing. Unfortunately, for authenticated encryption, we found a drawback, which we want to improve, that because basically you want to calculate the authentication tag, you have to send all the data first before you can get the encrypted and the data. And because the memory is limited, it kind of the kernel limits you to encrypting like 64 kilobytes, I think, something like that. Yeah, but with simple stream ciphers, it's kind of like the kernel doesn't keep the data, so you send a small buffer, you read it back, then you send a small buffer again, and kind of advance through the stream. Yeah. Any more? Going once? Yes, everyone wants lunch, right? Thank you very much.